mentioned that one too.
Yeah, I mean, that's what they were talking about a second ago, and that's why we're transitioning into that right now. Is that the very definition of 2 to a function, 2 to a power of t, is, as we saw before, you can say natural log e, since that, of course, is the inverse of each other, literally what it is, and you can you can do this, natural log of 2 e to the natural log of 2t, sorry, e to the natural log of 2t. These are automatically equal to each other, which is why I was 100% wrong the other day when I said you had to do it differently. He's exactly right. You could write it in any particular way. As a matter of fact, yesterday, if you kind of were wondering where the equation came from, the n equals n0, by the way, listen to what he said earlier, we have a rate that is proportional to the thing itself, and that's why we're dealing with exponents essentially in a nutshell, that essentially what it came down to was 1/2 n, with the number of half-lives, okay? From that, I can kind of, let's ignore the n and the n0 right now and come right down here and go 1/2 n. Well, that, let's go ahead and make that 2 to the negative n, right? And we'll go, let's call that the natural log of e, because that's the same thing right there, which means that this is the same thing as e to the negative natural log of 2 times n, right? Now all we have to do is figure out where n is the number of half-lives. How can we easily figure out the number of half-lives? How much time has progressed? And what is the time of the half-life, right? This top being a variable, by the way, I was just talking about this happens all the time in calculus and absolutely all the time in physics, in which we use the lowercase 1 to denote some variable and the uppercase 1 to denote some constant. This thing is not changing, this thing is. So if the half-life is 4 seconds and 8 seconds have progressed, that's 2 half-lives. So this is equal to n. Yes? Yes. Now, I'll come down here. I'm showing you all this because it directly translates to an AP test question that I'm going to show you in just a second along these political lines. And I thought it was kind of fascinating the way they did it. All right, so we take that n and we go e is negative natural log of 2 times t over t to the 1/2. And then we recognize that these are all constants. And since those are all constants, let's make a new constant out of it. And of course, that's where we get e to the negative lambda t. And what does lambda equal? Natural log of 2 over t to the 1/2. Okay? Now, that all being said, what he said is that exponents can be written in a bunch of different ways. We started out here at the top of this particular conversation, starting with this, the idea of the half-life. But why is it half-life? I don't know if you've ever thought of this. Why is it always worrying about exactly 1/2? 1/2 is arbitrary. It could be any fraction whatsoever. As a matter of fact, we could go, well, let's reverse this. Let's reverse this. And instead, I'm going to go, I don't want natural log of 2 to be here. Okay, so what can I do so that natural, that's a kind of a weird thing to have as a constant. So the nice thing is, if I didn't have natural log of 2 here, okay, this was 1 instead, then what I said yesterday, and now I'm re-remembering why it was there, lambda would just be 1 over t to the 1/2. It would literally be the inverse of whatever the total half-life is. As a matter of fact, the best way to think about it then would be the frequency. A higher frequency would incur more of these particular half-lives in the exact same amount of time. Well, how could I possibly do this and eliminate the half-life and do all this? Well, all I would do is this real quick. If I eliminated this, okay, then at the half-life's time, we would get what? What would the function be whenever time is half-life's time? E to the negative 1. Punch e to the negative 1 into your calculator. This would mean at 1, and actually it's not a half-life anymore. I'll explain what I mean in just a second. At 1 period of time, what do we get?
3, 6, 8.
So I'm just going to go ahead and round that to say, basically, when you do this, what you're actually doing at the beginning is, instead of doing a half-life, you're doing a, not a very clean name, a 37%. life of it, if that makes sense. Okay, and the nice clean thing about that is now, go to the AP test real quick. Do you guys have access to all of like the multiple choice that it has on here? Or do I have to like assign them before you can see
I
it?
think you have to.
You have to.
Do I have
assign
to?
it all, yeah.
I didn't know if you could look at them anyway, because I will try to assign a bunch of them, not for homework purposes, but instead for you guys just to.
Will you assign like? Do you mean like in general, or will you assign like
What are
ones
you
from
doing
like
to me right
past
now?
chapters?
Do I know?
Will you assign?
I'll
stuff?
assign whatever. I mean,
Okay.
it takes a little bit of time for me to do, so I can't just like I don't want to willy nilly just go. You know, I'll do the whole thing, but yeah, I can certainly
Okay.
with some of them. Okay, so we are. This is the other reason I wanted to pull up the AP test, is I kind of wanted you to have a really good fundamental before we get into chapter 30. I wanted you to have a fundamental understanding of what you would need on the AP test and what's kind of gravy, as it were, today in finishing today's lesson.
So we're gonna finish.
We will finish Physics 2 today.
The half-life is for half of it to decay, right?
Yes.
Not for half of it to be left.
No, it's half of it left. It is telling you how much is left when
So,
it does that.
For the 0.37, there's 0.37 left.
37% is left, yes.
Okay.
So these are the units. You'll notice it's 9 to 15. It doesn't start in 1 because AP 1 starts in 1. And here we have unit 15, the very end of what we've been talking about. So just highlighting this real quick, you can kind of see in this chapter. Quantum theory, wave-particle duality, we discussed in chapter 27. Bohr's model was discussed in chapter 27. Emission and absorption, spectrum of chapter 27. Black-body radiation was actually at the beginning of chapter 27. Actually, I'm wrong on that. Hold on. That was 28. This was 28. That was 27. That was 28. Both of these two were actually 27. Compton scattering is also in 27. So the first 6 sections we're pretty much already done with. Skipping ahead, radioactive decay that we were discussing yesterday, and we can look at some of those multiple choice on there so you can kind of get a sense pretty quickly of what I would imagine all of you guys would be pretty decent right there. And then today we will be talking about fission, fusion, and nuclear decay in just a second. So radioactive decay, where's the one I was looking for? Well, I'll just show you some of these real quick, and then we'll do the one I was going to specifically go to. Let's try to zoom so we can see all of this, maybe? No? You're not going to let me? I thought I had all of this on my screen when I did this. All right, here you go. So cobalt-60 nucleus undergoes radioactive decay, but remains cobalt-60 nucleus. What type of decay has occurred, and what evidence do you have reasoning? I think the first answer you can answer, what type of decay would have to occur? Gamma has to occur. So skipping right down here to C and D. Gamma decay has occurred because the emission of photons means the number of protons and neutrons didn't change, or gamma decay has occurred because the emission of an antineutrino means the number of protons and neutrons did not change. Which one is it? It would be C. C is correct, yeah.
Beta's the neutrino one.
Yeah, beta's the neutrino one, which we'll talk a little bit in greater detail today. Just doing a handful here. Well, actually, here you go. A student write down the reaction for tritium, or hydrogen-3, decaying into helium-3. Another student claims that this reaction is written incorrectly. Which of the following supports the claim that the reaction is written incorrectly? The change of the number of protons in the nucleus violates the conservation of charge. True or false? These, they're fine. Yeah, they are fine there because, of course, we talked about the fact that what actually ends up happening is that in this particular case, you have one more proton, because as the electron skips out, one of the neutrons becomes a proton in that particular case. Okay. Change in neutrons within the nucleus violates the conservation of the nucleon number. No, it doesn't fit whatsoever, because it actually stays exactly the same. Creating a neutrino without creating an antineutrino violates the conservation of neutrino number. Nope. Here it is. Creating an electron and a neutrino without also creating an antiparticle violates the conservation of lepton number. It is D in this particular case. We will talk about those conservational lepton rules here a little bit later today. That's where we're gonna have. One more and we'll be done. This one's a pretty easy one. A plutonium-210 atom decays into a lead-206 atom. Which of the following must have occurred? That's all you're looking for on the AP test.
Oh, mine's cool.
Yeah.
Dang.
We've gone from 4 to 88 to 80. So there you go. Okay. They're not. And that's what I was trying to like get a sense of showing you this today, so that when we are having these conversations, it's great that you're asking me these extra questions. I love that, but I also want you to know kind of what you're expected to know versus what is kind of a little bit extra. All right. So where did the one go that I wanted to? I think it's the second one right here. Yeah, this took. Okay, so it's sort of this one, but you'll notice how the AP test presents it, and I had not thought of it this way, and so I kind of wanted to talk to you right here. You'll notice that right here it says the sample of sulfur-35 atoms decays to e to the negative first, or 37% of its original number in 126 days. The sample of 10,000 sulfur-35 atoms, approximately how much of the sample is remaining after 6 weeks? Okay. So this one, just do test taking strategies here, right here. Okay, so you start at 10,000. Which one's automatically out?
14.
14's already out. Okay, 37% of 10,000 would be 3,500. Okay, and that's going to occur at 126 days. You've only gone 6 weeks or 42 days. So is it going to probably get to 37%? Which means that one's out, which automatically means boom. You got your C answer right there. So you could trial and error that one. That being said, this next one, you could also sort of trial and error, but is kind of fascinating. So here we go. We have a list in this table of 3 isotopes, X, Y, and Z. The decay constant is the initial, also shown as the decay constant and the initial number of atoms in each prepared sample for each isotope. Where sample is prepared at time 0, which of the following ranks time X, time Y, and time Z, at which each sample is expected to have 1,000 E-2 or 135 atoms. Now, them presenting it like this was a little bit wonky to me, and what I realized later on that they are doing is, like I said, is that E to the second is nice because it means it's 2 of the 37s that I was doing just a second ago. That is essentially what's going to work out to 0.37 times 10 to the second, or we've taken the 1,000 down to 37% of that, 370, and 37% of 370 is 135. Okay, so what is the ranking of the times? Well, let's look at this table real quick and see if you can't discuss in your group what it should be, and then we'll talk about it at the end, and then we'll move on. Helps guide you. The first way I did it was just essentially test taking strategies as opposed to solve. I didn't solve any exact numbers when I did it. It's asking these 3 samples start with a certain number, here on the right side, have decay constant you're seeing right here. So which of them basically will take the smallest amount of time to get down to 135 2 of the constants. Yeah, you can't say 135 because it's essentially 135. I would not do any. You should not need a calculator to do this. And yet.
And yet. And that one will take longer than that.
Now, you don't need a calculator, but let's do this real quick. What is the decay constant?
Lambda.
It's lambda. Okay. Another way to look at that is kind of the decay frequency, because it's s to the negative first. So a higher decay frequency means what? Less. It takes less time. If it's a higher number here, it would take less time. If you do invert it, so if you invert the number of this guy right here, what do you get? If you invert that number, 1 over 0.01, what do you get? 100. What is that units on? Seconds. What would that 100 seconds be? The amount of time it would take for Or in other words, that's the amount of time it would take to go to 37% of its original amount. Does that make sense? So this one takes 100 seconds. What do these guys take? 50 seconds. Now, forget all of that. You should very quickly be able to go, which one of these is absolutely going to have the smallest time? Why? Absolutely. So why?
Because it has the highest decay constant with like a less number of atoms.
Yeah, it's the fastest going. So absolutely, if you just use that, watch here. Run down here and go, nope, nope. It's got to be one of those two. Why is it definitely this? Why is it definitely not this? Why is Ty not going to equal Tz? Yeah, and then if you want to do the math of it all, you can see actually this. They do a good job of explaining it, and again, I thought about a lot this morning during this is mostly what I spent my advisory on. So they kind of do the thing that you just said. Ty is obviously going to be the fastest because it has the faster decay constant and the fewer number of atoms entirely. But there's this kind of cool thing that actually e to the negative first, or 37%, is roughly speaking 1 over 2.7, which is kind of an easy number to memorize if they do this, because you'll notice that that means after one decay constant, it should be divided by 2.7. So this is not a random number they chose here, because how much should be left after one decay constant? Yeah, it should be 1,000 is left, right? And how long did it take to get there? What's that? It would take 50 seconds, right? Then another decay constant would take it to get to 370, and a third decay constant would take to get to 135. So how long did it take this sample right here to get to 135? 150 seconds. Whereas this guy, which started with a smaller number, how long should it take? Well, how long is it going to take this 1,000 to go down to 370? One amount of time, which was what for this? 100 seconds. And then to go from 370 down to 135 should take another one. So how much should this take? 200 seconds. So which one should do it faster? Z, even though it starts with 2,700, should actually get down to that number faster than X does. How you feeling? Okay, the highlight of what I'm trying to get to right here is that it looks like the AP test does not use like the standard half-life equation like we are using, okay? But they are in fact using the exact same equation at the same time. It's this. Our equation is this. Half-life. That's also their equation. But what's been different? So what do we do to actually do half-life? What's that? No. If to use this equation, how is our equation the same as theirs, but we're using half-life and they aren't? Hello, sir.
Today is a very important holiday.
Well, thank you so much.
You're welcome. Have a good one.
You got me fine. All right. Wait, it's cherry.
Cherry's the best.
Not the best.
Okay, well, apple.
All right. What's the difference? Lambda. For us, lambda is what? To do half-lives, what's lambda?
It's T
That's our lambda.
Yes.
What is their lambda? We use the exact same equation. This is what's said when the other guy said you can write the exact same setup in multiple ways. Basically, we're using half-lives, or our equation comes out of this right here. Their equation comes out of this right here. What's nice about using their equation, of course, is that they're always going to just do E, and this is simply going to be, this right up here is the N number. Right? If I take their version of a half-life, their 37% life, and put it right there, then T over that is just going to be the N number in that particular case. I don't know if we're confused or bored of it all or what it is, but I'm losing you guys, so off we go. All right, chapter 30. If you see me skipping around a lot, I researched this again earlier today, and I say researched this. You can find it yourself on, darn, I already got rid of it. Pull this up here. On Google Classroom, if you look under chapter 30, it says explicitly what I am going to cover in here in terms of reading. Non-testable, 0.4, 0.5, 0.7, 0.8, and 0.10, or if you want what is testable, is sections 1 through 3, section 6, and section 9. And the reason why those are what is testable is so that I can talk, I think section 6, I don't know if it's 6 or 9, is those conservational laws that you talked about just a second ago, that you can kind of get down to into that. But this topic is, I've said before, that physics 2 is walking up to the edge of a topic and going, holy crap, look how deep this actual topic is. Thermodynamics is so much deeper than I thought it was, and then walking away from the edge. We do the ABCs of thermodynamics, and then we walk away from it. Same thing is true of electricity and circuits. We've just really done the basics, hitting that stuff. Okay. Obviously, never more so is that true than when I get to the elementary particles and the standard model of what is understood in physics here today. So take that with a grain of salt. So what are we going to be covering? We will be covering, I definitely moved that out of the room. Okay, we will be covering nuclear fission, nuclear fusion, the 4 fundamental forces, which will be a very quick and easy conversation because you already know it. The explanation of the rules implemented, the conservation of the baryon number, and the conservation of the lepton number, and then finally the last thing that we will definitely hit is essential features of the electroweak theory, standard model, and grand unification theories. And that way, if you guys ask extra questions today, and number one, I don't know the answer, at least you feel somewhat better by the fact that you don't actually need to know it for the test. And number two, it's just kind of beyond the scope of this particular class as it stands right now. All right, question. Nuclear energy and elementary particles. The first part of this is continuing off of what we talked about yesterday, and that is Q values. It's also what I said that in actuality, all all nuclear reactions don't actually have a nuclear amount of energy. There could, in fact, be nuclear interactions happening in this room right now, albeit they are very, 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 very rare. They still can actually happen on this level. They're just not going to, spiral out of control. What you're looking at right here is the way to create nuclear fission. Specifically, this can actually happen with multiple elements up there, but we're going to focus on specifically uranium. Okay, uranium-235 is your big one. Okay, and what you do is you bombard uranium-235 with neutrons. And if one neutron hits a uranium-235, as you'll see in this equation, we step up to uranium-236. That little star right next to it means it is unstable. And naturally, it will break apart into daughter cells. Now, the reason that's an X and a Y right there is because actually there is a lot of possible options on what it potentially breaks down into, on what is the easiest to get out of that particular process. So, for example, here is one possible option that could come up. I bombard a neutron into a uranium, and I get 141 barium and 92 kryptonite, along with 3 neutrons. So why is uranium so special? Uranium's so special because it takes one neutron bombarding uranium right here to start this particular process. And the most important piece of this particular uranium is at the end result, you kick off 3 more neutrons. Why is that important? Well, because that means that the type of interactions, assuming you have a plethora of uranium actions, are in fact exponentially going to increase, right? If I bombard one with one, I get 1 interaction. And then I get 3 interactions, which cause 9 interactions, which cause Okay, crap, 27, and now 81. And all of this is happening so ridiculously fast that this is a chain reaction that spirals out of control. So an individual interaction by itself it'll cause a lot of energy for the reaction, nothing noticeable, but you spiral all of that stuff off very quickly, obviously big boom real fast. And if you measure all the numbers, you can of course see you got 236 on the left, 236 on the right. But what you're also going to notice is that the total mass number on the right is in fact smaller than the mass number on the left. And remember our Q values from the other day. This is basically the thing we ever did. I can add up all the Q's on the left, all the Q's on the right, find the difference in mass and multiply by that 931.5. And I can get that the Q value coming out of this one interaction is 200.4 mega eV. Yes?
I remember that it happened over why that when the mass on the right was greater, you had to have more kinetic energy than you would have had to produce that much mass. Why did you have to have more?
Well, it's just like an activation energy. It's not going to naturally, it's got to get the energy from somewhere, right? Okay. That negative number essentially says, I've got to get over the hill. I've got to get enough energy to start this particular process and go down the hill. It's kind of like, like activation energy is regularly described, right? As a matter of fact, I think you guys know this, cellular respiration. Most good interactions that we have in the human body have an activation energy. Why is it nice to have an activation energy? Because then you can control it with enzymes and how fast it goes. The main way that your body controls how much cellular respiration happens in your body is temperature. The temperature kind of sets the baseline specifically of where this is at, and thus how much needs to jump up to the top. And we've talked about before, that's why fevers are so ridiculously dangerous, because as that temperature goes up, this thing happens in way, way, way more often, progressing more energy, progressing more temperature, and potentially causing that temperature to spiral out of control and burn your brain up, and obviously that would not be good, which is why everybody goes to the hospital at 103 degrees Fahrenheit, because that's way too high. We gotta cool you down, you're gonna burn your brain up. Moving on. So, this is exactly what I was describing just a second ago. You got a neutron coming on, it hit 235, you got 236 right here, which is now unstable and in an excited state. So what's gonna happen is you're gonna get those protons pushing against each other. I got too many neutrons, it's gonna rip apart, and as it rips apart, we get 2 daughter cells out of it and 3 neutrons in that particular setup. And as I said a second ago, in nuclear reactors, this is a regular thing that occurs. Now you will notice I like this picture because it actually shows 3 different possible options of uranium splitting up. Actually 3 different ones, because I don't think any of these were on the first one. We got strontium and xenon, you got yttrium and iodine, you got neodymium, and is that strong barium? That's not strong barium. That's SB up the head. 51. Yeah, antimony. Of course it is. Yeah, so, but in all cases, you're creating 3 neutrons. So, what do you do in a nuclear reactor in order to fix this? Well, what they do is they have people regularly monitoring this, and when it spins up at the very beginning, they're starting this chemical reaction, and they have in there basically measures of whether or not Q is stable coming out, whether or not the amount of energy, or whether or not it's getting too big. If it's getting too big, what that means is that the number of neutrons is in fact exponentially increasing. So what they have in here are what are known as control rods. And the control rods are relatively simple to use and do a very simple thing. All they do is they're a material that absorb neutrons. So what they're looking for is simply this, okay? In a reaction, you're going to create 3 neutrons. So the goal when a nuclear reactor is stable, meaning the reaction is happening, it's happening, is they want net only 1 neutron to come off the reaction. Why? Well, because 1 neutron will make this, and then if this shoots out 3, we absorb 2 of them, 1 will do this, and now we have a stable amount of energy specifically coming out, regular amount of energy coming out. I can spin up this, I can kind of let it go above 1 and raise it to the amount of energy level that I want coming out in a unit time. And then as soon as it's at the level I want, I literally physically lower the control rods further in so they absorb more and more neutrons until it's a stable amount coming out. Now, the names of these are absolutely going to be on the multiple choice. and they're kind of actually probably backwards of what you might think a power plant regularly uses. Okay, the reproduction constant K is a simple measure of how many total neutrons are coming off of every reaction. And the ideal is 1. When K is 1, the reactor is said to be critical. Now, unlike that, what probably inspires in your head, that is a good thing. If a reactor is critical, that is not a bad thing. Critical is good. It's stable. It's doing exactly what it's supposed to. It's functioning exactly as it's supposed to. We are at an absolute correct level. Now, bad is arguably the next to, one definitely more so than the other. Okay? Next is subcritical. Subcritical, K is less than 1. So net, obviously we have some neutrons coming off. You're not going to get a fraction of a neutron coming off. But basically if you had, this just means if you had 100 interactions, we have less than 100 neutrons coming off of those. Probably the control rods are too low. I say too low, but actually this is not necessarily a bad thing either. If the nuclear power plant saw that they have too much energy coming off of their particular reaction, you would purposely make it subcritical so that you would lower the amount of energy until it's right where you would want it, and then you would take those control rods further out until once again, okay, I can read how much energy is coming out, I'm getting the right amount of energy out, and so now we're back to being n equals 1. And obviously the worst one of that is K is greater than 1, because supercritical is what is happening when you are putting out more neutrons than 1. Obviously, so what is K naturally, like if it's left to its own devices? K is 3. Why is K naturally 3?
They make 3.
Because that's how much comes off of every single interaction, and obviously that is supercritical, and supercritical would make Big Boom very quickly. Okay, so obviously supercritical, you would not want that to last a long time, but like I said, at the very beginning of the interaction, you would want it to be supercritical so that you're spinning that up, letting the energy get to kind of the level that we want. Once it's at that level that we want going up, you would want K to go back to 1, yes.
Can you explain what subcritical is bad again?
I mean, it's not inherently bad. All it means is just that the reaction's dying. Okay. As a matter of fact, amongst the many safety features of a nuclear power plant, one of them is simply a circuit that basically does this. If power goes out, meaning it is incapable of like kind of monitoring and we don't know what's going on with this chemical reaction, right now what happens is pretty much every freaking control rod that is in that substance goes straight into the nuclear stuff, and we go subcritical super hard. And what does that mean? It goes way back. It goes from being basically a nuclear reaction to now the whole darn thing is stable. It is very stable. There is not going to be a reaction whatsoever in that process, and now we're all good. All right, so moving on. Nuclear reactors, I mean, I think this is they're a little bit of the book's propaganda, I'm not going to lie to you, but they do a pretty decent talking about this. A fission, where's it? That's what they were talking about. Most reactors in operation today use uranium as fuel. Natural uranium contains only about 7% the uranium-235 isotope, with the remaining 99.3 being uranium-238 isotope. This is important operation for reactors because uranium-238 almost never undergoes fission. Instead, it tends to absorb neutrons and produces neptunium and plutonium. For this reason, reactor fuels must artificially be enriched so that they can contain several percent of uranium-235 on that particular front. I was wrong. I said 3. I'm sorry. On average, 2.5 neutrons are emitted off of every fission event. So K would actually be not 3, but 2.5 in that particular case. To achieve self-contained and sustaining, we talked about this already, so I didn't go into that. Okay, nuclear reactors. Fission in nuclear reactors, heat, molten, or water depends on the system, which is pumped through heat exchange and a thermal exchange transferred to a secondary system. The water is converted to steam, which drives the turbine energy. This is just what I've said before. Essentially, all power plants just run off the electricity principles we discussed before. What do you need to have electricity? Spin a magnet, right? Spinning a magnet creates magnetic flux. Magnetic flux, as we discussed before, changing a magnetic field is what creates current. So in a nutshell, pick a type of power, you're basically spinning a magnet, right? If you think about anyone, what does coal do? How does coal work? How does coal power plants work? What do?
Burn it.
They burn it to do what?
Heat the
Heat up steam. Steam comes up, hits the wheel, spins the wheel, we get electricity. Basically, power plants are almost identical to coal. The only difference between a nuclear power plant and a coal power plant is how they're heating up the steam. Okay?
Is everything just spinning?
What's that?
Why is all power just spinning things? I know it's just the electricity conversation, but
Yeah, it's just an electricity conversation because you have changing magnetic field. It is Faraday's law. Faraday slash what's the other one? It's the negative n change in iota b over delta t. Yep, is equal to EMF. Essentially, that is what it is. It's why a motor and a generator are literally the same thing, right? A motor, if you spin a motor, it'll create electricity, right? It's the exact same thing. You just spinning a magnet. Or in other words, or like spinning a loop of wires inside a magnetic field will also work. Okay. Given concerns about greenhouse gases, global climate, this is where I was talking about a second ago. Energy, despite the advances in technology, one of the most green things that we have is nuclear power plants. Honestly, the main thing that nuclear power plants have to deal with right now is just simply social conversation. Is what people believe about a nuclear power plant. The fact that people are scared of nuclear power plants is the main reason why we do not have them more prevalent throughout the United States. Quite frankly, they are more than likely the easiest source of energy that we have moving forward, but people are afraid of the big boom. So thanks a lot, Chernobyl, and people not paying attention there. All right, so we talked about fission, big thing splitting apart. Now fusion. Fusion in the sun. Fusion in the sun is obviously two light elements coming together, and as far as the science of it all, you're going to get Q values in a lot of the conversation that you just got done in 29. Here it is in a nutshell. Okay, here's fission in the sun. They'll take two hydrogens and create a deuterium and beta decay. You'll notice that is in fact that's what right there? Positron, which is why you have a normal neutrino and not an antineutrino. And then of the deuterium that you just had right there, that can also combine with a hydrogen via fission to create helium-3 and gamma radiation. I told you the other day that gamma radiation is regularly coming from the sun. Boom, there you go, regularly happening. And then, of course, you can get hydrogen plus that helium-3 to form just normal helium, also in beta decay, right here. Now, beta decay, by the way, doesn't go very far. Beta decay doesn't shoot out a lot. The main thing, of course, what of all of these energies that you're looking at up here, what's the main one that's getting to us? That guy right there, that's a photon. That would be gamma. That's not light. No, that would be gamma radiation. That's the stuff that's going to cause. Yep, that is going to be electromagnetic radiation. Okay. What you're not seeing in this, I'll talk about in just a second. But of course, you can also get through this process helium-3 and helium-3 to helium-4 and 2 hydrogen at the very end. If you combine all 4 of these possible interactions, what you'll notice is that a lot of the things like deuterium is just an intermediate step. It's used in another reaction, so there's not a ton there. Helium-3 is also an intermediate step. It can combine with both hydrogen by itself and with itself in order to form helium-4. So in a nutshell, the sun turns hydrogen into helium, and all of these processes have a very positive Q value. Yes?
How do you know the gamma's there?
How do you know that gamma radiation is there? What do you mean?
Like, oh, yeah.
No, light wouldn't be it. Remember, light is a very specific subsection of radiation. Gamma's not that. Gamma's way higher. But the fact that we have gamma radiation coming off of the sun would cause that particular reaction. Yeah.
So, in like specifically the bottom reaction, they're combining, but also the particles are flying off. So how do they decide it's fission versus fusion? Because both things are happening. There's combining and losing of.
Well, all 4 of those are going from lighter to heavier. I mean, I suppose you can make an argument on the last one that hydrogen is smaller than helium, but the big thing that's being created there is the helium-4, which is heavier than the other 2, and those 2 hydrogen are just going to come back into the circuit and be used like right back up here. So net, what we're looking at, I see what you're saying with these being lighter than this. Ultimately, when you look at these 4 equations and combine them all together into a net process, like I said, hydrogen is turning into helium, so light things are turning into heavier things. In total, which is why it can be considered fission. Yes.
Where did the positrons and neutrinos go?
They're short range into not very far. Into the star itself, into localized areas around there. We'll talk about beta in just a second. I want to try to hustle a little bit here. I did too much of the stuff at the beginning. There you go. Here's the Q values of three of these particular processes. So you can see in total, I say 3 different processes. I don't think that, hold on a second. Let me make sure I'm not lying to you here, because I could be. Okay, so this was fusion in the sun. The fusion reactions, these that appear most promising for the construction of a fusion power reactor are the 2 isotopes of hydrogen, deuterium, and tritium. So these 3 that you're looking at right here are the most promising interactions that could potentially allow us to cause a fission reactor here on Earth. Now, what is the main reason why fission, oh, I screwed this up, my apologies. Fission, big stuff getting smaller, is more prevalent here on Earth than fusion. Why don't we use fusion? So hold on a second there, because what do we have more of? The big elements or hydrogen? We definitely have a crap ton more hydrogen, which is honestly the main reason why this is more alluring to us. We would much rather be doing this. Why aren't we?
It's hard to do.
Why?
Activation.
You need a huge amount of activation energy. And what does the natural process have in order to have the huge activation necessary required to get this started? Temperatures of the sun. So what is going to be our main struggle in creating the fission? We don't want to be around temperatures of the sun, but we're going to need temperatures of the sun to make this happen. Yes.
But why would we want fusion? Like, what would that do for us?
So the answer to that question is we have a ridiculous plethora of hydrogen. As a matter of fact, there's hydrogen in the air right now in the form of water. And quite frankly, through, I'm going to say this wrong. I would say like diatrolysis. That's not right. Electrolysis might be probably the best word. Through fairly easy methods, we can very much split hydrogen from oxygen. Not that big of a deal whatsoever. If you ever watched The Martian, fantastic movie if you've never have, he does it with a very limited amount of supplies on Mars. Obviously, that's a fictional movie, sort of, but the science that is done in that, specifically electrolysis, very possible for us. So we have a huge resource of material available to pull this off. So if we had the technology, energy would be free. If I had a piece of technology here that could separate hydrogen out of the air, and then I could do these things, I've got free energy here, right? Right? I have to go to the gas station to get gas. I don't go to the gas station to get hydrogen. It's right in here, right? It's right in here. It's right in. We have a plethora, a ridiculous plethora of the resource necessary to do this. We just don't have the technology, science, and understanding yet to do this. So that is the decided advantage. If you've ever played any Fallout, okay, one of the things you'll regularly hear, and they're talking about their power sources, and obviously it's a fictional world, blah, 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 they're using nuclear power sources, is they are all fusion power sources. They're basically saying the idea is that they've got hydrogen and they just plug it onto the wall, and I don't need the power company anymore, right? I can power my house for free just using this technology and maintaining it. Essentially, if you want, it's a nuclear version of a stream in my backyard, and I could use a stream to power electricity for my house as well. So that's kind of the allure of the whole prospect is how clever it is.
So, like, with both of them, you get energy out of both of them.
Mhm.
It doesn't, like, take energy to make fusion happen.
Well, okay, so net gain, you're going to get some out. The difference is this, okay? Number one, fission, while we have a good amount on Earth, if you guys go to the internet right now and try to get the resources necessary for fission, how's that going to go? They're going to put you on a watch list. You're not going to get the materials. Things aren't going to go well because obviously you screw that up, big boom, okay? That being said, if theoretically, if it was made safe, we had the technology for fission, is there anything the government or anybody could do to keep you from the resource of hydrogen? No. Be like removing, like, literally they have to remove water from you in order to do it. So you have all of the resource, all the time that you would ever need to pull off and have that amount of energy. Of course, the nice thing about fission is that the insert energy to make the whole thing spit out energy is practically nothing at all. The activation energy is like nothing. You put in a neutron, a little bit of kinetic energy, boom, boom, boom. It chain reacts out all on itself. Fission, on the other hand, the reaction is kind of like this. It's kind of like saying, like, okay, this process will put out this much energy, right? But to get this much energy, you have to start with, this much energy in order to get going. So are you going to gain energy out of it? Sure, but you're putting in, if you will, like, you're putting in 1,000 joules to get out 5. Right? And I should specify, let me just say that differently. You're putting in 1,000 joules to get out 1,005. So you are gaining energy in total, but you have to put a lot in to do it. So the way that you put all that energy in to begin it is you need a very high temperature. Naturally, that occurs at the sun. The hypothetical idea they have for that right here is what's known as where is it at? So this is their kind of main idea that they're using magnetic field and a vacuum chamber in order to actually pull off. This is, where is it at? What's it called? Darn it. It's got a cool name. A tomac. One device is called a tomac, a donut-shaped geometric toroid in the figure above. The device is a combination of 2 magnetic fields, one to confine a plasma inside the donut, and a strong magnetic field is produced by current in its windings. A weaker magnetic field is produced by the current in the toroid. The resulting magnetic field lines are helical. In this configuration, the lines spiral around the plasma and prevent it from touching the walls of the vacuum chamber, getting energy basically built up faster and faster and faster and faster until it's at the right temperature in order to pull it off while protecting. So this is, again, still hypothetical, but that is kind of the general idea. What's that? No, this is still, at least they have, and they certainly could. I mean, government does research that doesn't tell its population all the time. It could be working right now, and they would not tell us until it is very close to, like, a normal person could keep it stable all the time. All right, I'm almost done, actually. So the reason why this conversation is a very quick one is because while I'm talking about some new stuff with fusion and fission and all the like, there's really no new conversation here. As far as calculations that you would have to do on the homework, it's going to look extraordinarily similar to the Q calculations that you're doing on your homework already. Okay, you're going to measure the mass of the uranium atom, the neutron. What's the mass of these 2 daughter cells and the 3 neutrons? There's going to be a difference. It's going to decrease in mass. You're going to find the Q value out of that. Boom, boom goes to dynamite and move on from there. Same thing with the fission reaction. Fusion reaction. Man, I don't know why they made those words too similar. All right, next, a very quick and fun conversation because I find it hilarious that the Physics 2 textbook, this is the first time, by the way, if I were not me, that you would be hearing about these things. Okay, these 4 things right here. Since I'm me, you heard about it chapter 4 last year, so this is a dumb conversation. What is electromagnetic force? It's protons and electrons attracting, protons repelling, electrons repelling, binds the atoms and the molecules. Okay, what is gravitational force? All mass attracts all other mass, holds the planets together. What is weak force? Involved there, like we said yesterday, involved in the mechanics of beta decay, specifically beta decay. And finally, the top one right up there, strong force, binds the neutrons and the protons in the nucleus together. Yes?
So is weak force basically just, we know there's movement going on and we don't really know why, so we're going to give it a name?
There is more to it. There's much more to it than that. And again, I border on my ignorance here, I'm sorry. But there's I read the textbook this morning, and I don't want to break down the textbook that you can read. Highly suggest that you read that section of beta decay. But essentially, it boils down to yes, there's an interaction here. Now, if you read chapter 30, if you are fascinated by this stuff and you want to go further in depth than what I'm explaining right now, I just read chapter 30 also this morning, kind of going through it, and there's some fascinating stuff in here. But even when you're reading chapter 30, you're like, but how do they? And the book says from the very beginning, essentially what I said at the beginning of class, like, listen, guys, this is a very complex, in-depth, large subject that we are giving. Basically, all chapter 30 of is a tour of the facility of what this giant conversation textbook-wise is. Okay, so there's no way they could spend all the time to explain why these things are what they are. So we're going to approach it from again, the experimental physicist side of things and go, it is what it is. This is what we've seen it is. These are the rules. We're going to say these are the rules. And then obviously, if you want to continue forward and learn about why and why and why and why, well, now you're on the cutting edge and you can go from there. All right, to that end, these four forces are all associated with a particle. I'm now going to transition into talking about the particle idea of physics. In the particle idea of physics, you're going to ask me what a lot of these particles are and how they measure them. And I'm just going to say what they are kind of goes hand in hand with this whole conversation, which is very in-depth, and so I'm not going to do a good job of that. As far as detecting them, there's a whole lot of things. I think the book does a good job of telling you when to, like I read in the textbook earlier, Lillian was asking me yesterday how we measure a neutrino and that type of thing, and actually, or when the positron was measured, and there's a couple times they show in there. I think the neutrino was discovered in 1937, I think is what it was, and I think that the positron was 1956. Maybe those are backwards or off, but it's in the textbook if you're curious on those, a little bit of to talk about. So, elementary particles. These are the particles that essentially relate to their respective forces. Now, the easiest way to explain this is electromagnetism, because you understand electromagnetism the best. All right, let's start simple. I've got a positive here and a positive here. What do they do? They repel. All right, so that is the electromagnetic force. Now, do they repel immediately? No. At sea. So what is traveling at sea? Well, you can either, from the classical wave theory, discuss it in the form of that it is an electromagnetic wave that is traveling here, or in the terms of the particle theory, what is traveling between these two? Photons. So the argument of the electromagnetic force from particle theory is this. This one shoots out a photon. This one shoots out a photon. They then go over to the other one, and so what do? They repel. They repel because of being hit by the photons, right? Because does that happen immediately? No. How fast does it happen at sea? That's essentially the intermediate particle that exhibits the force that we're talking about, okay? The respective forces along these times are gravitational force, gravitons, that I've got a mass, something else has a mass, and it is a graviton that travels to another thing that I then absorb. I absorb its graviton and thus am attracted to that particular thing, and vice versa from my mass over to the other mass. And that works with gluons between neutrons and protons, and it works with bosons with the weak force and that conversation. Now, as to the weak force conversation that you were trying to proceed towards a second ago, while weak force in terms of what we have discussed is such a small subsection to this understanding, there is a whole chapter and stuff devoted to it specifically in the particle theory. It's in your textbook. There's a whole section. I read it this morning. I don't know if I could even portray it to you, but here you go. So this is essentially what I was saying right here. You've got an electron going this way, you've got an electron going that way, and what interacts between these two electrons? We'd expect them to repel. Why does that repel? Because of like what they would call a virtual photon. Now, why is it called a virtual photon? Because the photon would be emitted by this electron here, but absorbed, so it was not actually going to exist anymore, causing them to go in opposite directions. This is what's known as a Feynman diagram to understand things a little bit better. Yes?
Okay, so if I have a proton and an electron, my proton shoots out a photon, and the electron like absorbs it or whatever.
Then it would attract.
And then they attract.
Different
But
photons.
that doesn't make sense.
Yeah, there would be different photons.
What? But that still doesn't.
So, I'm sorry, okay? Listen, I'm essentially doing a tour of calculus for people that know ABCs. What do you want from me here? Okay? And quite frankly, I don't. I mean, I've been teaching kindergarten physics for all of my last 17 years. I'm not well versed, of course, in calculus level physics. You get the analogy. All right. What's that?
I just don't get why.
Okay, I know you don't get it, and I hate that you don't get it. I hate that I can't explain it to you. But it would be like this. You're in chemistry, and you go to your chemistry teacher, and you say, chemistry teacher, I don't understand why the d orbital looks like this. Can you explain it? They could. It would take about a year and a half, which is why they send you over to me to teach it to you in a year and a half, so you understand why the p orbital is what it is at a, I don't know, probably even 30-40% level, even after you've learned everything that you have. That's essentially the answer. You're asking me a question that would take me probably a year and a half to learn, much less explain it back to you in this particular thing. It's not entirely that I don't know, but also that it's such a gigantic concept. It's not a quick answer that you're looking for me here, if that makes sense. And I don't have good context of rules that you already have well established to be able to work these things together. So I apologize. I wish I could do better. I don't think you're going to understand today. You're just going to have to take me at my word and go from there. And then as you head into later physics, kind of like build your knowledge up and go, oh, okay. And then you can come back and teach me. And I'll be happy to learn from you because I'll be ignorant in that case. What to do?
What's a quark?
Okay, let's continue. All right, so the elementary particles and fundamental forces, this is a chart that goes with all the stuff. We actually did this ratio. I kind of told it to you generically first on. I said, what's the strongest force? It is, in fact, the strong force. That's the power of 1. Relative to the strong force, how strong is the electromagnetic? Times 10 to the negative second, or about 1/100th of the strong force. Okay, the weak force is times 10 to the negative sixth. Okay, and of course, the gravitational force, when we say it's weak, it's ridiculously weak. Relative to these two, it's times 10 to the negative 31st. We talked about this. Now, the next thing I want to point out here, obviously the far right side is what the last slide was. These are the mediating particles that travel between the two. Okay, the range of force is actually something we've already discussed a little bit. That electromagnetic and gravitational are long. You'll notice they're proportional to 1 over r squared, meaning that essentially they have an infinite range, although it does take time for their forces to travel that particular range. Okay, both the strong force and the weak force are really, really short range. The strong force, as we discussed the other day, has a range of 1 femtometer, meaning that my neutrons are not affecting your neutrons. As a matter of fact, my neutrons in one atom aren't even affecting the neutrons, the protons, 1 atom over, because it's too far away in that particular. They're only affecting within that particular nucleus itself due to its short range. The weak force is even shorter than that. It's 1,000th of a femtometer. Here we go. This, I believe, is Paul Dirac. He was the invention of all of the antiparticles. He invented this. Basically, he was doing work on energy and essentially created some. Oh, I know what it was. Not energy. He was trying to marry together the ideas of relativity and quantum mechanics into one cohesive unit. And as he did that, he found particles with negative energy, and he was very irritated by this. So somebody comes along a little bit later, looks at his work, and says, well, let me propose an idea that would have negative energy, and thus the invention of antiparticles. Antiparticles like the positron have been measured. We have, in fact, seen it. Positrons are probably the easiest one to measure because actually you can kind of understand how we did this. It was done, who did it? It's a famous guy that did it. I read it earlier. I'm sorry. So it was, but essentially it's that magnetic field situation we talked about the other day. If the magnetic field is going this way, undefected would be gamma, right? Alpha would go up this way, and electrons would go down here. But what should be different between alpha and an electron? They should go at different paths because they have different masses. An electron should be a much sharper path. So if you detected something that was along that path that also was going in the positive direction, that would mean it has the exact same mass as an electron, but has a positive charge. Thus, whatever the thing that is, you could name that the positron, because it has the exact same charge, just positive in the opposite direction.
First, because it didn't fit the naming scheme.
I don't know. I don't know if they discovered what order they discovered them particularly in. But you'll notice normally, other than the positron right up here, the normal notation for antiparticles is a bar right above it is currently understood and theorized that every particle has an antiparticle. Okay.
Anti-neutron.
Yes. Well, let's get to that.
Okay.
Here is the current list of particles as it stands in the modern theory. We have the electron neutrino, the muon neutrino, the tau, and the tau neutrino. You'll notice all 6 of these are classified as leptons. Okay, hadrons on mesons are pions, kaons, and etas. Okay, all of which you have never probably heard before, I'm guessing. Okay, baryons, you will see 2 that you very well know. Baryons would have protons and neutrons, and also lambda, sigma, xi, and omega. Now, if you struggle with kind of that, again, you can get to, I'll get to that in just a second. We'll come back. I thought they had the picture on here. Darn it. Oh, there it is. Okay. So this is, this particular picture was done by, guys, stop laughing. I know it's complicated. I get it's
conservation of strangeness.
Oh, yeah, 100%. Yeah. I don't know why they named it strangeness. They made it worse. That's fair. Yeah, this stuff's already confusing enough. Let's call things like color and strangeness. That won't make it worse. All right. I'm almost at the end of stuff I have to cover, and I'll try to knock it out quick. But I'm trying to remember that picture importantly. Okay, this drawing represents the tracks of many events obtained by the bubble chamber photograph. Strange particles of this guy. Okay. And kappa particles coming from, this would be pions, negative pions, and protons in this particular process. Let's see here, where is it at? Basically, you can see all different particles that are interacting in this particular case and what they came out. And how would they know these? Well, they're going to analyze paths. They're going to analyze the path to figure out radius, to figure out forces, to figure out masses on all of these respective things and the size they're in. Now, conservation, I'm sorry, I'm out of time here. But to figure out which things are allowed, which equations up here are allowed, they have come up with 2 conservational laws. Okay, the first conservational law is the conservation of the baryon number. The sum of the baryon number must be the same before and after the process. The baryon number, if you come back here, can be found right here at B. A lot of these particles just have 0, making it very easy to conserve. But the most important ones to note on baryon numbers are protons and neutrons are both at 1. So you can trade a proton out for a neutron as long as you conserve the correct amount of baryon numbers. Along with that, the other conservational law is the electron-lepton number. Specifically, that can be found right here. The lepton number can be electron or muon or tau, and all of these have, you'll see this is 1. These guys have 1 for mu and 1 for tau. That number must be conserved. And the final number that you're looking at over there on the far right side is the S number, or the value of strangeness. That's the conservational laws we had. Okay, real quick to end what you were asking earlier, what is a quark? Okay, so at one point in time we believed atoms were the smallest thing. Then we believed that electrons and protons and neutrons were the smallest thing. Now we've gone down to quarks, and all of the particles I just said were actually made out of some combination. Most of them are made out of some combination of quarks. For example, it is believed, you'll notice the charge on an up quark is positive 2/3 elementary. So it is believed that a proton is 2 up quarks to give us 4/3 and 1 down quark to give negative 1/3 for a total of positive 1e. When you break those quarks apart, that is the reason why you can take an electron and a proton and combine into a neutron, because they are divided by several different quarks, and when you split those quarks up, they will make the opposite one in that case.
Top this, bottom this, charm.
Oh yeah, there's all. It goes into. Oh, man, I wanted to talk to you about this real quick. Essentially, this is. Okay, you talked about the weak model electromagnetic. The weak interaction is ridiculously important because it actually governs the stability of basic particles of the matter. What we find that more important than just radiation is the fact that something is stable boils down to what the electroweak theory is doing. That's all you needed to know. So I'm going to stop.